Hi, I'm Chen-Hao. I would like to present my work called Denoising Likelihood Score Matching for Conditional Score-Based Data Generation. So here is the overview, and I would like to first introduce the background about score-based generating model, and then I will talk about the conditional score model, which is the main topic of this work. So what are score-based generating models? This kind of model estimates the log gradient of the probability density function, and it notationally look like this. We call this score function, and it is actually a vector field with each vector pointing to the high density region. So as you can imagine, for the data generation process, we can randomly initialize a point in the space and work along with this score function, then we can get the data point here. And that was the basic concept for the sampling process. And the formulation here is known as linear Boole dynamics, and which tells us that we can update a sample using the score function with some randomness. And now we have the sampling algorithm, but how to estimate the true score function. So formally, given ID sample points, our goal is to estimate this term using a parameterized model. And now the questions are how to compare these two vector field and how to formulate the loss function. So intuitively, we can overlap them at each point in the space and calculate the difference. And this gives us our objective function, which is the expectation of the square Euclidean distance between these two. However, the second term in the loss function is actually computationally intractable because the calculation involves the summation over all samples in a dataset. So actually, the calculation of this loss function is not scalable to a dataset size. To resolve this issue, Pascal-Vincent proposed an alternative loss function called Denoising score matching, and he proved the equivalence of these two loss functions with a constant difference. And the new loss function here is computationally efficient because the second term here can be easily computed because it has simple form 1 over sigma squared times the difference between the clean sample and the perturbed sample. And that was the basic framework for unconditional score-based generation process. But for some application scenario, we may need conditional data generation process. Here I provide some examples such as class conditional generation in painting or colorization. So for this task, our goal is to obtain the conditional score here. And intuitively, we can model this term using a conditional score model trained with DSM loss. However, this method is very inflexible. So an alternative method called conditional score decomposition was introduced. It basically states that the posterior score can be decomposed as likelihood score plus the prior score. And with proper parameterization, we may see that it is actually a mixture of the score model plus the log gradient from a classifier trained with cross entropy loss. And here are some related studies. The most famous one is PPGN. They applied this formula to real-world dataset. Another one is a recent work from OpenAI, and they found that this term here is inaccurate in practice, so they add a scaling term to enhance the log gradient of the classifier to improve the fidelity of the generated sample. So in this work, we evaluate some study, and we would like to further investigate the reason why the posterior is inaccurate. So we conduct a thought experiment and compare 4 different methods with the 2 we introduced in the last page, and the third one is the joint modeling method we just introduced, and the last one is the oracle score, which can be derived using a closed form formula. So as you can see from our experimental result, the first 2 methods generate inaccurate score function. However, the third one generate very accurate score function. So, however, the third one is undesirable due to its inflexibility. So we would like to improve this too. And if we compare these three kind of method, we may find that the main difference is the cross entropy loss here. So so this actually tells us that the density estimation loss may not be enough for the gradient estimation task. So our idea is relatively simple. We would like to directly matching the likelihood score during the classifier training. So this is our loss function, which specifies the L2 distance between the log gradient of the classifier and the true likelihood score. However, the second term here is computationally intractable, as we discussed before. So we formulate an alternative loss function called denoising likelihood score matching, and this loss function can be efficiently calculated because the second term here is the prior score, which can be estimated using a score model with a single forward pass, and the third one is the log gradient of the Gaussian perturbation kernel, which has simple form here. So actually we can involve this DOS and loss during the classifier training to enhance the classifier's ability to predict the true likelihood score. So this is the experimental result. Our method improves a lot. Also, we test our method on the CFA10 and CFA100 dataset, and we see that our method outperformed the baseline method on several key metrics. And so in this work, we propose a new kind of loss function, and we experimentally examine its effectiveness. Thank you for listening.